Okay, now we're starting to record, and we're going to be talking about logic theory. It's very, very important, and you will see its use quite a bit during this class. First, what we do is we define the constants. What are the constants in the logic theory? We have two constants, true and false. Those are called sometimes Boolean. Okay, I'm trying to kind of capture all of this so when you read in some books Boolean, that's what they mean. Boolean constants is something true or false. 0, 1 is fine, okay? True or false. Now from there now we define the constants, two of them, and now a variable, I call it logical variable or Boolean variable or sometimes proposition. It is a variable P that takes the value true or false. Okay? So any statement that can be true or false is a proposition, is a logical variable. For instance, these are examples, very straightforward examples. Today is Tuesday. It's a proposition. It could be true, it could be false. I am 25 years old, proposition. Discrete mass is easy. We can disagree on that. Some people might say true, some people might say no. 2 plus 5 is equal to 10. Miami is the capital of Florida. 5 minus 2 is equal to 3. So these are propositions. You can ask me, okay, give me examples of things that are not proposition. Is here, what is your name? That's not a proposition. Now, if you tell me my name is John, that's a proposition because you might not be telling me the truth. See the difference now? Do your homework, it's not a proposition. When you say, I did my homework, that is a proposition, which could be true or false. Mind your business. 5 plus x is equal to 10. This is not a proposition. It's when we assign value to x, it becomes a proposition. Good? X plus y greater or equal than z, that's not a proposition. So now, we define the constants, we define the variables. Now we're going to define some operators or operations. Connectives, they call it as well. They apply to simple propositions, and your book is calling it atomic proposition, to create compound proposition. Sometimes we call it Boolean expressions. So you can hear Boolean expressions, you can hear compound proposition. It's really several simple propositions connected together with operations, logical operations. Here, we start with the first one. The first one is the negation, the not. Now, there are two ways of defining what an operation does, either through statement in English, or you can use what we call truth table. Here I have only one proposition, P, that could be true or false. Not P is the negation of P. When P is true, not P is false. When P is false, not P is true. That's called the not operations or the negation. Now, here are propositions. Today is Tuesday. I am 25 years old. Discrete mass is easy. 2 plus 5 is 10. Miami is the capital of Florida. 5 minus 2 is equal to 3. Okay, I want you to tell me, I hid this in part on purpose because I need to have a kind of communication between you and interaction here. What is the negation of today is Tuesday? Anybody can jump in and answer that. What is the negation of today is Tuesday?
Today is not Tuesday.
Not Tuesday.
Today is not Tuesday. Don't tell me today is Wednesday.
Mm-hmm.
Okay? Because you might be wrong. You might think, you can say today is Thursday. It's possible, right? But the negation of today is Tuesday is what? Today is not Tuesday. Got it? What's the negation of I am 25 years old?
I am not 25 years old.
I'm not 25 years old. Don't say I'm 18 or 17 or 25 or say. So what's discrete mass is easy. The negation discrete mass is not easy. 2 plus 5 is 10. The negation is 2 plus 5 is not equal to 10. You just put a bar across the equal sign here. Miami is the capital of Florida. What is the negation of this?
Miami is not the capital of Florida.
Okay, don't tell me what Jacksonville is the capital, because you're wrong that way, right? Okay, so you don't correct me because your correction might not be wrong, might not be true. You just say Miami is not the capital of Florida. 5 minus 2 is equal to 3. Again, not equal to 3. Here are the answers. So you put not capital, not equal to 10, not easy, not. When here we just put scratch this and across this here, and okay. So that's a first operation. Now the AND operation. And you see, I used this AND last week, and maybe next time I will restructure the class so that we start with the logic theory first, and then we go to the others ones, because we will use this quite a bit. Now, back to the negation. The negation only uses one variable. Now we are using two variables, and that's the AND operation. The AND operation is true when both are true and false otherwise. Look at the table here. And it's called conjunction. Conjunction and so true, true produces a true, true, false, 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 true, false. So it's true is only when both are true. Agree? So now here's an example. Dominic is from France and he lives in Ohio. So how do I put this in terms of logical expression? I call P, Dominic is from France. Q, Dominic lives in Ohio. Then this one can be translated as P and Q. P and Q. Now, I have two now different kind of ORs. One is called the inclusive OR, and one is called the exclusive OR. Now, let's see the OR here. The OR here is true when at least one of them is true and false otherwise. See, true, true, false produces true, false, true produces true. It's false when both of them are false. This is called the disjunction. Disjunction. The exclusive OR now, and we use this symbol for it, it's true when only one of them is true and false otherwise. You see that? True, false gives you true, false, true gives you, and here gives you false, and here gives you false. This is called the exclusive OR. Now, from the context in the language, you will understand what it was meant. Was meant an inclusive OR or an exclusive OR. For instance, no outside recess if it is raining or if the temperature is below 25. Then if both conditions happen, you will not have a recess, right? If both happen, you won't have a recess. So that's an inclusive OR. A prerequisite for Math 510 is Math 120 or Math 230. So if you want to go and enroll in 510, if you have already taken these two, they will enroll you for sure. This is an inclusive OR. Here's an example of an exclusive OR. Lunch comes with soup or salad. So you're not going to fight the restaurant, tell them you said OR and I need both of them. No, he will give you only one. All right. A car dealer offers 2,000 cash back or 2% financing. You won't ask for both of them. This OR is exclusive. Or this OR is exclusive. Now, remember now, this is really close to the union in the set theory. And this one is the intersection in the set theory. Very, very related, okay? And this one here is the complement in the set theory. right? Now, the implication. This is very, very important, very important. We say that P implies Q. And the easiest way really to keep in mind and remember, and you will never go wrong if you remember that, we do not allow truth to imply false. See here, I boxed this. You do not allow truth to imply false. All other options are true. True implies true, yes. False implies true, yes. False implies false, yes. The only one you say no is true implies false. So P is the hypothesis and Q is the conclusion. Now, there are so many ways of saying the same thing. You can say if P then Q. You can say P implies Q, if P, Q. These are in red the most used ones, okay, in logic theory. But those are also the same thing. Q whenever P. Q is necessary for P. P only if Q. Q if P. P is sufficient for Q. Now, what I want you to do later on, I'll give you some examples, is when you want to deal with these kind of conditional propositions, if you have a language like this or this or this or this, first turn it into P implies Q before you do anything. Then the thing would be much easier, and you will see in a bit here what I meant by that. Okay. True or false? I want to give you like a minute. All of you just write down on a paper, line by line, whether it's true or false, and then you will see. You check your answers when we reveal the hidden box there. And when you answer the question, put on the side whether it's true implies true or true implies false or false implies true to see how you got that answer. All right, I think we're good, right? So you need some more time. First one, is it true or false?
True.
It's true, and it's of the form true implies true, right?
Yeah.
Good. What about number two?
True.
It's
True.
also true.
Yeah.
Right? False implies false.
Yeah.
Now, I want you to pay attention here. I'm not saying 12 equals 15 is true. I'm not saying that. I'm not saying this is true. I'm saying the implication is true. Okay, so look, if you tell me 2 equals 5, then I can add 10 to both sides and get 12 equals 15. Right? Okay, what about number 3?
False.
True.
False.
True.
True.
That's true.
True.
False implies true is true.
Yep.
Okay, what's the last one?
False.
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 That's false because this is a true, and true does not imply false. Okay? Here are the answers. True, true, true. This one is false because truth, T implies F is false. Okay? So again, pay attention. Don't get confused. We're not trying to prove that 12 is equal to 15. We're not trying to prove that. We're trying to say the implication is right. The logical implication is correct. Now, and you will see why I want you to be trained to do that. is to turn it into if P then Q, or P implies Q. That's the thing, okay? Here, John gets scared whenever he flies. See, here is used whenever, right? I'm going to turn it into if P then Q because I can do more manipulation on this than on language like that. Okay. Tell me how can you write this if P then Q?
If John flies, he gets scared.
Good. Yeah. Yeah. What about number 2?
If you were born in the U.S., you are a citizen.
Yeah. Yeah. So you will see later how it's much easier to manipulate these things when they are of the form P implies Q. You will see that just in a bit here. What the third one?
To access the internet, it's necessary to have a valid password.
So if you have a password, you access the internet.
Yep.
If you access the internet, then you have a valid password. Okay? So once you do this, I said it the other way around. So it's necessary to have a valid password to access the internet. If you access the internet, then you have a valid password. Okay? Now you see the importance of turning something into if then or P implies Q. Here are 3 propositions that can be made out of an original proposition. So you have P, Q, not P, not Q, okay? And here the implication, and you notice here, true does not imply false, okay? You notice that here. So if you finish the table here, the way I did it here, Q implies P, that's called the converse. The converse, Q implies P. Look at it, Q implies P. True implies true, yes. False implies true, yes. True implies false, no. False implies false, yes. Now look at this, not P implies not Q. All right, so I'm going to go to probably, let me see here. Okay, so now because I need to use my my pen here. Okay, so no, now we need to do this. Not Q implies not P. Not Q implies not P. Not Q implies not P in this direction, see? False implies false? Yes. True implies false? No. See? No. False implies true? Yes. True implies true? Yes, I got that also. Now the inverse is not P implies not Q. Not P implies it in this direction now, see? In this direction now. F implies F? Yes. F implies true? Yes. True implies F? No. True implies true? Yes. So once you have that, then you watch it now. I'm going to go back to the okay, I'm going back here. So now you notice that these two are the same. These two are the same, and these two are the same. This is extremely important to remember, the contrapositive and the implication itself. Those are equivalent. They produce the same results. So down the road, when we talk about proofs, proof of theorems, sometimes we cannot prove P implies Q, but we can prove not Q implies not P, which is the same. Okay? But look at the converse and the implication. It said they have nothing to do with each other. Okay? Now, here will example where they ask you to state the converse, contrapositive, and inverse. Okay? The converse, contrapositive, and inverse. Jennifer comes to school every time there is going to be a test. All right, so this is the language that is given to you to confuse you. Don't play with this language here. Turn it first into P implies Q. So first write a proposition in the form if P then Q, or P implies Q. If there is going to be a test, then Jennifer comes to school. So now you see, let me go to the slideshow again here. Okay, now you see this one here. That's P. Then that's Q. Then I put it now of the form P implies Q. I put it in the form P implies Q. Now it's easy for me to see the converse, the contrapositive, and the inverse. Why? Because the converse is Q implies P. The contrapositive is not Q implies not P. And the inverse is not P implies not Q. Can you see everything, or the pictures are hiding? Okay. Okay, so fine. I think we can do like that. Okay. Okay, that's better. Converse P, Q implies P. See, Q implies P. So you easily can write now, if Jennifer comes to school, then there will be a test. Very easy now. Don't use whenever. Don't use this. You get confused. In the last 25 years, I taught this course. Students, if they don't turn it into like this, they get confused. And the contrapositive, not Q implies not P. Not Q. If Jennifer does not come to school, then there will not be a test. Okay, and so on. You can do the inverse the same way. Very straightforward. Okay, so that's why I want you to always turn it into if P then Q. Okay, now note, if a conditional proposition P implies Q is true, it is contrapositive, not Q implies not P will be true, always. But its converse, Q implies P, will not be necessarily true. The converse is not necessarily true. Here's an example. The conditional proposition, if n is prime, then n is odd, right? So now, if n is not odd, n will not be prime. That's the same thing, saying the same thing. Okay, that's the contrapositive. But the inverse, or the converse, if n is odd, does it necessarily n is a prime? No. 15 is an odd number, it's not a prime. 21 is an odd number, it's not a prime. 49 is an odd number, it's not a prime. Okay? So to understand this contrapositive, you can say, okay, if I live in Dublin, so I am in Franklin County, right? So the contrapositive, if I am not in Franklin County, then I am not in Dublin. That doesn't need proof. But if I am in Franklin County, is it necessary that I am in Dublin? No. You could be in Hilliard, you could be in Columbus, you could be in Worthington. Correct? Okay. Okay, so now I need to get this out here again. Okay, now we are going to introduce another one. It's called the biconditional, if and only if. So you can hear if or biconditional like that. Again, it involves by implication it involves two variables, P and Q. And P biconditional Q is true when both have the same values and false otherwise. See, true, true, you get true, false, false, you get true. Now, it's not difficult to prove that P biconditional Q is the same as P implies Q and Q implies P. You can use a small table like that. You can see that they are the same. Okay? So far we introduced the negation, we introduced the or, we introduced the and, we introduced the implication, and we introduced now the double implication. Okay? Any questions so far? Are we okay? Now, we are going to put some definitions here. A compound proposition is tautology if it's always true. If it's always true, we call it tautology. If it's always false, we call it contradiction or unsatisfiable. If sometimes it's true.
Hey, get in here.
Yes? Is it a question? Maybe somebody was talking to somebody else. Okay. So, let's see here. All right. So, again, tautology is when the proposition is always true. Contradiction when the proposition is always false. And then when you have a proposition that is sometimes true, sometimes false, it's called contingency, okay, or satisfiable. Sometimes it's satisfied, sometimes it's not satisfied. Now, you can make a small table like that and see that P and P implies Q is always true. Is always true. And that is called the Modus Ponens proposition. See, you have P is true. Okay, let's see, explain this to you like it's interesting. Let me show you how that's going to do. Okay, so here, what we have, you have P is true, and you have P implies Q is true. This is true, and this is true. I'm going to say that Q is true. If P is true, and this one is true, Q cannot be false because P does not, truth does not imply false. Then Q must be true. Okay? So if P is true, and P implies Q is true, then Q must be true. Okay, that's called Modus Ponens. Contradiction, this is an example of a contradiction. You can just kind of go over the table here and work it out. You see it's always false. Those are some of the tautologies, and those are their names. Okay, now if I have to ask you about any of this in the test or something, I will produce this table for you. So don't get too scared of these names and things like that. Some of them are really easy. For instance, the hypothetical syllogism, if P implies Q and Q implies R, then P implies R. Okay? This one we did. The Modus Ponens we did. Let's do Modus Tollens. Here, what do I have here? I have, I'm going to write it down here. I have not Q is true. And I have P implies Q. I am concluding that not P is true. Okay, what here? Not Q is true, meaning Q is what? False, right? Now, if this one is true, then this one here is false. And you have P implies Q is true. Then P cannot be true, right? Because truth does not imply false. If P cannot be true, then not P is true. Then P is false and not P is true. Okay, so this is a simplification. P implies P or Q. See, sometimes in mathematics, we tell people, in arithmetic, we tell people that 3 is less or equal than 5. They can see that easily. But when I say 3 less or equal than 3, they say, wait a minute, that's equal. Okay, equal, then will be equal or less. Okay. Conjunction, okay, we have all of this. Okay. End of logic theory part 1. Any questions so far? It's very simple. What we did is we introduced the constants, true and false. We introduced a proposition. Any proposition that can be true or false is a proposition, is a logical variable or a Boolean variable, or that the same thing. Then we introduced operations. The negation, it takes only one variable. The and conjunction, it takes two variables. It's true when both are true and false otherwise. Then we introduced the disjunction, which is an or, and it's true when at least one of them is true. And we introduced the XOR, it's true when only one of them is true and false otherwise. And then we introduced the converse, inverse, contrapositive, and we said that contrapositive is always true when the proposition is true, the same value as the proposition.
So I know we used only P and Q for the demonstration here, but in real life situations there can be more than 2, right? So
yes,
then
we're coming to it. Good question. Yeah, we're coming to it. Yes. Yes, I'm taking you slowly because I don't want to hit you right with 3 variables. You say, wait a minute. No, I'm just taking it easy on you, so you can understand that and go. Yeah, there will be 3 variables. Now I will not ask you for 4 variables, but 3 variables. Yes, it's possible that you will have a question on a test that involves 3 variables. Yes. Now, logic theory part 2. That's logical equivalences. Logical equivalences. See, we don't say 2 propositions are equal. We say they are equivalent. That's the whole thing. If they have the same values, that's really why we use this here. All right. Logical equivalent is P is equivalent to Q. In some books, they use this. They use this. I don't know if I can write with this now. They use this symbol, the same thing. Okay, they're really the same thing. So sometimes if you use this or use this, for me is the same. Okay. Now, 2 compound propositions P and Q are logically equivalent. P is equivalent to Q if P and Q have the same truth values, which means P by conditional Q is a tautology. You can ignore this, just concentrate on this. If P and Q have the same values. Now, how do we prove 2 propositions are equivalent? Is we can use the truth table, Remember in the set theory, to prove 2 sets were equivalent, we use membership. And we use 0 that when when it belongs to the set, and 1 when it belongs to the set, and 0 when it doesn't belong to the set. Exactly the same thing here. So now this is very important, really important equivalence here that you need to remember. Why? Because working with the implication can be difficult when you have several propositions involved in it. But when you turn it into an OR, it's a lot easier, see? It's a lot easier. So what you have to do is P, Q, P and Q, they have two T's, two F's, T, F, T, F. What is P implies Q? Again, remember, we do not allow truth to imply false. Everything else is fine. What is not P or Q? Not P or Q. Here then or. True, false, true, true. And you see they are the same. Okay? Okay, now I'm going to give you some exercise here to work on your own, because otherwise you get bored here. You have to get busy here. These are the Demorgan laws, and we have seen them in the set theory. See, the negation of P or Q is not P and not Q. You negate each one and the or becomes what? And. Not P and Q is not P or not Q. How do we prove? I have this table to prove both of them, okay? So again, P, true, true, false, false, Q, true, false, true, false. And then I have not P. And maybe I should reveal not Q, huh? That's fine. Let me see. Okay, so you have P, you have Q is easy. Not P is what? When true becomes false, false becomes true, right? Very simple. Don't get confused. And not Q this. Now I want you to fill up this table, the rest of the table. Just fill it up. I give you 4 minutes. It's fine. This way, I see you understood what is and, what is or, the negation. See what you can come up with. Now, obviously, if your work is correct, let me see if I can. If your work is correct, these two will be the same, and these two will be the same.
Yes.
If you got them the same, then you're good.
Yes.
All right, should we start revealing the answers? You need more time? Okay, so let's start revealing the answer here and see what if you get it right or not. That's a P and Q. P and Q is true when both are true and false otherwise. P or Q, P or Q, P or Q, true when at least one of them is true. Now you need to negate this P and Q, that this becomes false, true, true, true. False, true, true, true. And then you not P or not Q, you see they're the same. Keep going and you find the answers. Okay? Here's the answer now. Now the awaited 3 variables problem. Here we go. Okay, so you asked about a problem where you have 3 variables. Here's a problem where you have 3 variables, is the distributive laws, and we have 2 of them. P and Q or R is P and Q or P and R.
Yeah.
P or Q and R is P or Q and P or R. Now, what you need, this here, we're proving this first one, okay, in this table. Now, what you need to do is, you have now 3 variables, then you have 8 different possibilities. In order for me to correct your answers easily, please make sure to start with 4 T's, 4 F's, 2 T's, 2 F's, 2 T's, 2 F's, T, F, T, F, T, F, T, F. All right? Don't start just randomly organizing them. It becomes hard for me to follow you, okay? So, and this way, each one will have, in the end, you will have the same answers. And what you do is, you look at the expression here. What do you have? You have P, Q, R, and you have Q or R, Q or R. Then you have P and Q or R. That's the left-hand side. Then you have P and Q, P and Q. You have P and R, P and R, and then you have P and Q or P and R, P and Q. So what I'm going to be doing here, I'm going to stop recording and give you 5 minutes to fill this up and take another 5 minutes break. So we will meet back at 7:05, okay? So 5 minutes to do this. Whatever you do it in 2 minutes, that's fine. You can take a longer break. So I'm going to stop the recording because it doesn't make sense to keep recording here. I'm going to pause it actually, if I can find where it is. Here we go. Pause. Come on. Okay, so let's see. I don't know where, I can't see you here, but that's fine. All right, so so again, as I said before, so these are the parts that involved in this expressions here. So you need Q or R. Q or R, so you look at Q or R, see true, true gives you true, true, false gives you true, true, false, true, 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 false.
So basically, how many ever number of propositions are there? We first convert them into like 2, putting the different ones into brackets and then solving the inner ones first, and then we do that way, right? Like if there are more than 2.
Say it again.
I said if there are more than 2 variables, so we put them into brackets. We solve the one.
Yes. Otherwise, yes. Otherwise, it's no. Yes, of course, yeah. So I mean, sometimes they give you order of priorities, but I really don't like it. If you have in some books, they will say. Okay, I'm trying to.
The order of operations?
Yeah, in some books they give you order of operation, but in some books they don't. So I will just, use brackets. This way you don't, because P and Q or R.
Yeah.
If you put it like this, it's not the same as if you put it like this, okay? So it's better just to keep the parentheses is better, yes.
Okay.
Okay, so if you do that, you continue this, you will see you get this answer, okay? And then when you get this answer, you just square this here and put another rectangle here, and you see that these two are the same.
Yeah.
So any question about that? Okay. Now here is another example, and I will, leave it to you now to look into all the details here, but that's kind of to tell you that the implication is not associative. In other words, P implies Q implies R is not the same as P implies Q implies R. They're not the same. So you have, if you have if you have an expression like this, P implies Q implies R, that's not a that's a confused proposition. It's not. There's no way to know what they mean. Do they mean P implies Q implies R, or do they mean this? And these two are not the same. And as you see here, you can do this table and you will find out that they are not really the same. Okay, so that's something you can practice. It's really simple. Again, look at what do we have here? We have P, we have Q, we have R, we have P implies Q, we have P implies Q and then implies R, we have P, Q implies R, P implies, see how we have the left-hand side and that's the right-hand side. So this is the left-hand side right here, and that's the right-hand side. And they are not the same, see? I pointed out to you that this is F here and that's true here. They're not the same. Now here is the logical equivalences, and this is really the same table as we have seen last week in the set theory, the same table. Now, how do you prove any of this? You can use the truth table. Okay, any one of this, you can use the truth table, you can prove it. See, we did this, one of this, we did this here, the distributive. And those other ones are really simple. Dominations, we did Demorgan. See, we did Demorgan. So now, those, they have names. Some of them are really easy. The commutative, we know that. Associative, we know that. Distributive, we know that. Demorgan, we know that. Sometimes we get confused with the negation, the identity, the double negation. So if a question about, okay, let's do that and I'll come back to this. So these are all the logical equivalences of interest to us. Now, sometimes you can prove without the use of truth table. And some students are good at that. Some, they find this to be difficult. I will not ask you to prove an equivalence without the table. I will not ask you to do that. But what I can ask you is, I will give you the proof, like in this case here, and you need to identify what happened from this line to this line to this line to this line to this line. In other words, what did I use from here to here? You can see I used the distributive law. See, P or not P, and P or Q, and P or Q. And now P or not P, that's true. This is the negation law. And then true and something is something, that's the identity law. And then here the Demorgan, and that's the right-hand side. Now, in this case, this would be given to you. Okay, so this will be given to you. Or what you have to do, you have to identify what properties I use from one line to the second, to the next. Okay, Any question about that?
Professor, can you go back to the previous slide? Can you talk a little bit about the domination?
Yeah. That's P or true is always true. And P and false is always false.
And false.
I mean, look, why P and false is always false? Because if P is true, true and false is false. If P is false, false and false is false.
Oh, okay.
See, why P, those are very trivial. Here, this one, identity. P and true is the same as P. Why? Because if P is false, you get a false here, which is the same as P. If P is true, you get a true, with the same as P.
Yeah, okay, makes sense.
And we have the same thing we did with the set theories.
Yep.
Same exact stuff.
Yeah, got it. Thank you.
P or P is always the same as P, very obvious. And P is the same as P. This is a double negation, not P is always equal to P. Okay? Any question about that? You can always, either these, or you can do that from the definition, or you can make a small table.
Yeah.
You can make small table for that, and you will find out that's the, so P or T is always true. Okay, so that's that. Now, this is an interesting concept. It's called disjunctive normal form, and students have some problem with it, but I'm going to simplify it as much as possible. So look at this as sum of products. Sum of products. See, the products, and look at and as product, and or sum. See this expression here? Sum of product, or variable by itself is fine. It doesn't matter. This one here is sum of product, but there's no sum. That's only one product. That's fine. DNF, disjunctive normal form. Here, example. We need to write P implies Q in disjunctive normal form, DNF. Sum of product. Here's what you do. Don't get confused. Don't get too scared of it. Let's make the table, the truth table for this expression, P implies Q. We know that true implies true is true. True implies false is false. True, true. Then I look at the truth value here. True, true, true. And this true is coming from P and Q. This true is coming from not P and Q. This coming from not P and not Q. And I put or between them, and I get the answer. So P implies Q is P and Q, or not P and Q, or not P and not Q. Now, obviously, there's a simpler example of this, because P implies Q, I showed you before, is not P or Q. That's another form. Sometimes you have more than one possible answer. That's called sum of product. Sum of product. This one is conjunctive normal form. That's product of sums. Product of sums. Product is multiplication, is and. Sums, or. Okay? Now, to think of it this way, the and is a multiplication, and or is an addition. True, think of it as 1, and if, think of it as 0. Not 1 is 0, not 0 is 1. Now look at this. P or Q or R, false. When is this false? P has to be false, Q has to be false, and R has to be false. Now, here, this expression, when is it false? P has to be false, Q has to be false, not R has to be false, which means R is true.
Okay. Yeah.
Here, when is this one false? When P is true, Q is false, and R is true. Now look at this now, an and here. P and Q and R is true. All of them must be true to get a true, right? True, true, true. Now, P and Q and not R, when is this true? When P is true, Q is true, and not R is true, which means R is false, and so on. Now, let's write the biconditional here in C and F, meaning product of sums. Product of sums. Okay. This is the way the book is doing it. I'm going to give you a second method in the following slide. C and F, product of sums. Okay, product of sums. So we are interested in of P biconditional Q. We make the table for P biconditional Q, and I will negate this now. Will negate this. I get this expression. Now, I look at the truth value. This true is coming from T. Now I'm doing it now in disjunction form. Okay, the sum of products, not the product of sums. Okay, sum of products. Okay, I get this, I get this. Then the negation of P biconditional Q is this. Now I do another negation, a double negation, and use the Demorgan laws, and I get this answer right there. Now this kind of a little bit long and confusing. What I recommend is doing it this way. Okay, so we need to have product of sums. Okay, product of sums. There's some baby in the background there. Okay, and this is an easier way. Look what happens now. Here I looked at the truth. True, 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 right? I looked at the true and put the and here, and then put or. Here, I'm going to look at the false. The false, false. Now, remember what I am doing product of sums. Then I have to have sums here. So for this to be false, I have to have not P or Q. For this to be false, I have to have P or not Q. Then I put an and between them, and I get this same answer that we have here. See how much easier to do it this way. Remember, you're doing product of sums. So you have to create the sums first, and then you put the product between them. Any question about that?
Yeah, in the first method, we were first evaluating two truths, right? Like we were checking if the evaluation is true, then we are calling it a normal form. But here in the second method, you were looking for false, right?
Yes. Yes.
So what actually is, I mean, I understand the normal form, but like why in one place we are checking for truths and evaluating?
Okay, because here, why I'm looking at the false here? Because I need to do sum of products. So for here, if you want to be here, false. When is this false? When P is, not P is false, what means P is true. See, P is true, Q is false, produces false. This means not P or Q. So if you evaluate not P or Q, it gives you false when P is true and Q is false. It gives you not P or Q, it gives you false. And here it gives you false the same way. Now, if I do now this and this, I will get the same answers here. Now, the question is here, when P is true, Q is true, P biconditional Q is true, this is false, this is false, this is false. So now if you take this expression now and make the truth table of this expression, you will find it to be false when you will find this, you will find exactly the same as this truth table. Exactly the same. If you create the truth table of this, it becomes exactly the same as this.
Oh, so does it evaluate the true conditions also, but just...
Oh yes, of course, yes. It will satisfy this, yes.
Okay, cool. Okay, that was my question. Thank
Yeah,
you.
yeah, it will satisfy. The same concept here. Okay, so if you take this, now let me explain something to you here since you asked about it. Okay, all right, let's do this. Okay, let's do this. All right, I'm going to go to the okay, so I'm going to give you something here. Okay, I'm going to put P, Q, and I have a function here, unknown, okay, unknown function. True, true, false, false. And I have true, false, true, false. Okay, are you following me? Now, I'm going to give you false, 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 true. And I will ask you to find me a function or an expression that satisfies this. Okay, what I do is I look at the true here. See, this true. True is coming from if. So I can put G equal not P,
yeah,
and not Q. Okay, so if I take this function now, okay, when is this function true? When not P is true and not Q is true. Otherwise, it will be false, right? So
yeah.
Otherwise, you get all these false. It gives you true when you have not P and not Q. Not P is true and not Q is true. This should be true, this should be true. Then the AND would be true, right? Which means P is false. So exactly now, if you take this function and put it here, you will find exactly the same answer. See, look.
Yeah.
Right? What? Here's not P. Here is not Q. Here is not P and not Q. Okay, not P. False. False. True. True.
True.
Not Q.
False. True.
False. True. False. True. And you have an AND here, right? Look. False. 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 True.
Yeah.
Got it?
Yeah.
Okay. So now, if I do, I need another space here. Okay, I can do it here. If I do the same thing as I did before, hold on here. P, Q, if I give you true, true, false, false, and I tell you to find the function G, so you look at the true here, see? This one is P and Q, and this one here, not P and not Q. If you take all of these two, you get the same answer, okay? That is sum of product.
Products. Okay. Yep.
Does that make sense now?
Yes, Professor. Thank you.
Okay. And that's the end of logic theory part 2. Did I forget anything here? No, I think we did. We did all right. Logic theory part 3, predicates and quantifiers. Predicates, yeah? Okay, predicate P over U is really a function from U into TF. It's a logical function, okay? U is universe, domain of discourse. Examples. Is prime n? That's a logical function from z, from positive integers into tf. So is prime 15? That's false. Is prime 19? That's true. Here's another example. Is perfect square 16? Is true. Is perfect square 8? Is false. Is rational x? Is rational 2.3? True. Is rational square root of 2? False. Very straightforward example. Now, here's another example. Q ABC is a squared plus b squared is equal to c squared. So that's a logical function from r times r into tf. Tell me now, is Q 3, 4, 5, is it true or false?
That's true.
Why?
3 square plus 4 square. 16 is 5.
Equals to 25. Good. What about the second one? It's not true, right? 2 square is 4. 3 square is 9. 4 plus 9 is 13. Is not equal to 16, right? So this is true. This is false. Okay, now we're going to introduce other operations here. They call them quantifiers. So the universal quantifier for any, for all, for any is this way. And remember last week somebody asked me about some of those here, and I told you that means for any. This one means there exists at least one. Okay. So when you say for any x in S, px, this one is true if px is true for every x in S, and false if it's false for at least one x. Here, the existential quantifier, there exists at least one. It's true what? If px is true for at least one x in S. False if px is false for every x in S. All right, it's your turn now. Check each one of this, give you a couple of minutes, and tell me whether it's true or false. Okay, so let's do one at a time. The first one, is it true or false?
True.
True? Yeah, n squared is greater than n for any n greater or equal than 2. See why I put 2 here? Because if you put 1, it won't work, because 1 squared is equal to 1, it's not greater than 1, right? That's why I put it from 2 and up. What about number 2? Is it true or false?
False.
False. Why? Because if you take 1/2, you square it, it becomes less than 1/2, 1/4. It doesn't become greater than x, right? Now, this will be true if x greater or equal than 1, it will be true, right?
Yeah.
What about this one? Is it true or false?
False.
For any x in R, x squared is different than 2?
False.
False. Why?
If I take x, it's a real number, right? If I take square root of 2,
It becomes equal to 2. Correct. Yeah, that's what we did here. You gave a counter example. See, you gave a counter example. That's what that did. What you did. What about this one here? For any n in Z, n squared is different than 2.
True.
true.
That's true. That's true. What about this here?
False.
There's x in R. That's false. Yeah, because this is completely positive. It can't be 0. See how the negation of this for any x, this is not satisfied. What about this? There's n in z, n squared minus 16 equals to 0. True or false?
True.
True. Good job.
True.
Good job. So here's the answer. So actually, here we have more than one. Okay. Counter example. Counter example. All right. Now, this is another one. There exists only one. And remember also last week, I think we addressed this. That's why I like maybe next time to do the do this chapter first and then go to chapter 1. Okay, so tell me yes or no, false or true. There is only one n in z. N squared is equal to minus 16 is equal to 0.
True.
True.
There's only one.
No, plus or minus 4, 2. So
Yeah, there's more than one, right?
Oh,
than 1.
yeah.
It's false. 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 What about this one here?
False. Was
That's false, right?
yeah.
There's no such an n that n squared less than 0.
Yeah.
What about this one here?
True.
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 Only, yeah.
One number.
One n that makes it
True.
8, which is
3.
3. Good.
Yeah.
All right, that's good. So you have the answers here. So when you say it's true, you give the answer, right? When you say it's false, you give a counter example. Okay. Now this is good. This is really easy to see. If S is finite, if S is finite, then for any x in S, Px means exactly Px1 and Px2 and Pxn. Okay. Now the negation of it, when you negate this, you negate each term here and you make it what? Or. See? And becomes or. So the negation of this is there is an x in S, not Px. Here. Okay, here you said for any x in R, x squared is equal to 2. We said that's false. Why? Because we found one x that makes it this equal, right? Okay, so that's kind of straightforward. And the same thing for there exists x in S. That means Px is equivalent to Px1 or Px2 or Pxn. When you negate this, you get the negation of all of this here. And I will come back to that in a simpler way just in a few minutes here. Okay. Negating quantified propositions, Demorgan laws for quantifiers. See here, if you want to negate this, the negation of for any, there exists x, and then you put negative here. You get the negation here. To negate there exists, then for any x, not Px. All right. What is the negation of this? Which is a true variable. This is a true proposition, right? For any n in z greater than 2, n squared is greater than n. What is the negation of this? There is an n such that n squared less or equal than n. See, this becomes less or equal than n, which is a false. The negation of true is false. The negation of false is true. What is the negation of this? This one is false, right? This one is false. We just said that earlier. There is an x in R, x squared plus 2 is equal to 0. The negation of this is for any x in R, x squared plus 2 is not equal to 0. See? See that there exists becomes negative, and then I reverse this, negated this. Okay, here are some properties of quantified propositions. So I will let you read those on your own. They're not really that difficult. The same thing here says some properties of quantified propositions. It's kind of worse. I summarized them for you, but they're really simple, straightforward from the definition. I put the proof here of one of these here. I put the proof here because I think you might have one questions on the homework about that. And I distinguished two cases, phi is true and phi is false. So I will also have you go through this on your own and and see how it's done. It's not that difficult. Now I need to talk about nested quantifiers. Nested quantifiers. Remember last week when we spoke about a function being onto, we said for any y in B, there is an x in A, y is equal to fx. See, and I used there exists for any, I used it last week too. So these are called nested quantifiers. Nested quantifiers. So you have two of them together, okay? So here is some examples here. There is a in z, there is a b in z, a squared plus b squared is equal to 14. Okay, and I'm saying that this proposition is false. I put a could be 1, 2, 3, 4, etc. And a squared is 1, 4, 9, 16. I stopped at 4 here because the addition here cannot exceed 14 anyway, so that's not applicable. Up to here, a squared is 1, 4, or 9. Then b squared is 14 minus a squared. 14 minus a squared is 13, 10, and 5. And those are not perfect squares. Those are not perfect squares. So you can't find a b here, all right? B squared is 13 or 10 or 5, so it's not a perfect square. Of course, you can find b in R, but I'm here talking about in Z. Okay, I want you to tell me true or false these propositions, these nested quantifiers.
First one is true.
The first one, is it true or false?
True.
True. Why? You take A.
3 square plus 4 square.
You get A3 and B4. Okay. And you can take A negative 3 and B4, or A negative 3 and B negative 4. All that will work, right?
Yeah.
Okay. This one here is also true. That's a triangular inequality. Okay, that's always true. How about this one here?
False.
False. Why?
It says for all x and for all y.
Yeah.
Is that correct? And
Yep.
so it's you could have 2 plus 2, which is 4, and that's not 10.
Okay, so what you did here, you gave me a counter example. Excellent. Now, another student might give me a different counter example. Okay, so in order to negate this, you just need one counter example. What about this here?
That one is true, the bottom one.
The other one is true, right? That's true, right?
Yes.
Because you got 3 and 7 is 10. Now, question: if I do like this, does it become true or false?
False, because there's
It
more
becomes
than one
false
option.
because there's more than one option. Excellent, excellent, very good, very good. We're getting there. So here are the examples. So here I chose this example. You gave me another example here, but that's fine. Counter example. See, when you want to prove there exists, you give an example. When you want to prove that for any is wrong, you give a counter example. Here's a very important thing I want you to keep in mind. If all quantifiers are universal, order is not important. It's commutative. For any x, for any y, is the same as for any y, for any x. If all quantifiers are existential, order is not important. There is X, there is Y, the same as there is Y, there is X. Now the problem is when they are mixed. For mixed quantifiers, order is important. It's not commutative. It's not commutative. Here, for any X, there is Y is not the same as there is Y for any X. Here's an example. For any X, there is Y, X plus Y is equal to 10. Is that true or false? That's true, right? Any X you give me, I can find a Y such that X plus Y is equal to 10. I will have to take Y equal to 10 minus X. Okay? So you give me X 100, I take 9, I take Y 90, and I get minus 90, and I get this to be equal to 10. Now, if I reverse this, swap these two, there is Y for any X in R, X plus Y is equal to 10. That's impossible. That's impossible. Don't tell me, okay, take 3 and 4, 3 and 7 equals to 10. Here you're saying for any Y, there is an X. In R, X plus Y is equal to 10. Is that true? No, sorry. There is a Y for any X, X plus Y is equal to 10. If you say this is true, I will ask you to give me that Y. You said there is a Y, give me that Y. You can't. Because no matter what we give me Y, I can find X that this one is not equal to 10. Okay? Now, negating nested quantifiers, that will explain to you the system, the concept. Look, for any X, for any Y, for any Z, H, X, Y, Z, negation. There exist, and you negate this. Look at this here. For any X, there is Y. For any Z, look what happened when you negate this. For any, there exist. There exist for any. For any Z, there exist. And you negate this. Don't forget, you need to negate this. Here's the last one. There exists for any. It becomes for any, there exist. For any, there exist. Okay? Is that clear? Is that clear what I'm doing here?
Yes.
Yeah.
Okay, good, excellent. Now, sometimes you were asked to translate statements into logical expressions. So here's a straightforward example. S is all students in your class. J, X has full-time job. HX, X has a hard copy of the textbook. AX, X can attend all classes. EX, X has an e-book, electronic copy of the textbook. Now, here's John does not have a hard copy of the textbook. Okay, so you put not H John. Because H John means what? John has a copy of the hard book, but we are saying here does not have. All students have hard copy of the textbook for any X in S, HX. Every student must have a hard copy or an e-book for any X in S, HX, or EX. There is a student who has both hard copy and e-book. There is a student, eh? HX and EX. The last example here, all students who do not have full-time jobs can attend all classes. So for any X, if you don't have a full-time job, then you attend all classes. See, we use here the implication. Here's another example. S is all students in your college. C is all courses offered. EXY, student X is enrolled in course Y. Here's a statement here in English. Mariam T is enrolled in Math 120. So you put E, Mariam T, Math 120, because that's what this tells me here. It tells me that student X enrolled in course Y. There is a course offered, but no students enrolled in it. So there is a course Y and C for any X not EXY. There is a student enrolled in Math 140 and Math 160, but not in Computer Science 120. See how we put it right there? Very simple. There's X in S, EX Math 120, EX Math 160, and not EX Computer Science 120. There is 2 different students enrolled in exactly the same courses. Okay, so there's X1, there's X2. For any Y in C, any course, X1 different than X2. Okay, you're not talking about the same student, and EX1Y is equivalent to EX2Y. So if X1 enrolled in Y, then X2 enrolled in Y, and vice versa. See how we can use the AND, we can use the OR, we can use the implication, we can use the double implication.
For the last one, does that imply that both students are in all courses?
There is 2 students enrolled in exactly the same courses. Yes, they are in the same courses, yes.
In the same courses, but
not
since
all
there's
courses, no, not all courses, no. The same courses.
Correct. I was just confused by the use of is it for any Y or for all Y?
Okay, we said for any Y, but look what would distinguish it here. He said if, that means if X, if this is true, this would be true. If this is true,
Okay.
you see what I'm saying?
Yes.
I did not put EX1Y and EX2Y. That
Yeah,
would be for
okay.
all Ys, yes.
Okay.
Okay? I think that's the end of it. Any question for me?
For our test, that's going to be on what you sent us, that Mobius, is that correct?
That is correct, and the proctor you will do the proctoring. They will have access to the test. I should be sending you the full information very soon once I make sure the test is being uploaded. And then what happens is when you have to register with proctor you and then make an appointment with them, and when at that time they would open the test for you.
Okay, thank you.
Is that clear? Okay.
Yes, good.
Any other question? So I'm going to stop recording at this point of time. I think we're done.